Of all the carboxylic acid derivatives, perhaps the one that resembles carboxylic acids the least at first glance are nitriles. So a carboxylic acid is a carbon double bonded to an oxygen, single bonded to an OH. And let me put those in different colors. So you have 3 bonds in a carboxylic acid to an electronegative element. And that's the actual thing that's in common between all of the carboxylic acid derivatives. So this is a carboxylic acid. Now a nitrile is where you have a carbon with 3 bonds to an electronegative element, but the electronegative element is not oxygen, it's nitrogen, and all 3 bonds are to just 1 nitrogen. And that is a nitrile when it's incorporated into a carbon chain. Sometimes you'll see this carbon triple bonded to nitrogen, and the triple bond won't be drawn in. It'll just be written CN. You can see that here. But there is a triple bond there. And sometimes you'll see that in ionic compounds, for example, sodium cyanide. When you have that in an ionic compound, this CN all by itself is referred to as cyanide. And so you can use a cyanide as a carbon nucleophile in synthesis questions. It's another way to make a carbon-to-carbon single bond, sort of like Grignard reagents and Gilman reagents, but this has a sort of functional group built in with that extra nitrogen there. Now, you might have heard of cyanide. Cyanide is a poison, and that's because the negative carbon here tends to bond to metals, especially iron and hemoglobin, and it takes the place of oxygen, so that even if you breathe oxygen into your lungs, the oxygen won't stick onto your red blood cells because the cyanide will be sticking there instead, and so you would suffocate, even though there's plenty of air in your lungs. It just can't hitch a ride on your red blood cells and get to your tissues. So these nitriles are often incorporated in biological molecules that plants make, or some snails make, for example, that tend to be prey, so that they'll prevent larger animals from eating them. Okay, well, that unusual feature, that those 3 bonds to a nitrogen, ends up creating reactions that are maybe not as intuitive as the other reactions we've seen, even though they generally follow a similar thought process. So let's try to think through some products of reactions with nitriles. Now again, with these, we can think of this from the perspective of synthesis, which is much shorter, but requires some prior understanding, otherwise it's just random memorization. Or we could think of it from the perspective of mechanisms. I'm going to do both, but first I'm going to do the synthesis, so that if you're not interested in the mechanism, you can scrub over it in the video into the next section where I talk about the synthesis for the next recipe. So here, you know that this carbon chain is not going to react. You'll still have these carbons here, and you have a carbon here also, even though it's drawn in. So those carbons will all stay there. The question is, how is this functional group going to change? What lithium aluminum hydride does, we've seen this before, it is a hydrogen nucleophile. So if we're just thinking of how this is going to, what product this is going to make, it won't get rid of the nitrogen in this molecule, but it will replace bonds to that electronegative element with bonds to hydrogens. Ultimately, the water is used to put hydrogens on the nitrogen. And so what ends up happening is, because in the product you wouldn't draw those hydrogens explicitly, they'd be implied, what ends up happening is you turn a cyanide, or a nitrile, into an amine. That's what the effect of lithium aluminum hydride is on a nitrile. Now, if all you're interested in is synthesis, you can memorize that. A cyanide will turn into an amine when you treat it with excess lithium aluminum hydride in water. But if you don't understand what's happening there, I'm sure it'll take extra effort to remember that, and you'll forget it more easily because it never made sense in the first place. So how can you make sense out of that? Well, let's draw it out. We have this carbon chain that's not going to react, then we have the carbon triple bonded to the nitrogen. Now that carbon has 3 bonds to an electronegative element, and so just like a carbonyl carbon, it's slightly positive. It's an electrophile. Our nucleophile here is lithium aluminum hydride. They write it as LAH. It could also be LiAlH4. That gives you something of a better sense of the structure of it. The aluminum is bonded to hydrogen 4 times. The whole thing has a negative charge that's stabilized by the positive charge of lithium. Because aluminum is a metal, it has very low electronegativity, and it gives its electron density away to these hydrogens, which become slightly negative. The aluminum is slightly positive. So these hydrogens are nucleophiles, and they can attack the carbon here, which is slightly positive. One of the pi bonds breaks, and the electrons goes onto the nitrogen there. That should seem somewhat familiar from the reactions of lithium aluminum hydride with the other carboxylic acid derivatives. So after that first step, what we end up with is carbon double bonded to the nitrogen. The nitrogen now has 2 lone pairs. It had 1 before. Now it has 2 and a full negative charge. And the carbon is bonded to 1 hydrogen, the hydrogen from lithium aluminum hydride. Now, this negative nitrogen is stabilized by the aluminum. So we still have this aluminum with 3 hydrogens bonded to it. And the 4th hydrogen already added, but there are 3 hydrogens there, and it's sort of sticking around with carrying along the lithium ion with it. And as we saw, the aluminum has very low electronegativity, so it's slightly positive. The negative nitrogen can attack that just to help stabilize the electrons in the charge. So the aluminum sort of sticks around to help stabilize that negative nitrogen. Okay. And the lithium is sort of floating around it. It's attracted to those slightly negative hydrogens. Well, so far we've added 1 of the hydrogens. We have excess lithium aluminum hydride. And so another lithium aluminum hydride molecule could sweep in and attack the carbonyl carbon. Just like before, the carbonyl carbon is still double bonded to an electronegative element, so it's still slightly positive. And so this nucleophilic hydrogen can attack it. So if we were drawing that in all over, we'd say, okay, these electrons come up and attack that, at which point the pi bond here breaks and the electrons go on to the nitrogen. So again, similar to the how this would react with a more traditional carboxylic acid derivative. So now this second hydrogen is going to add, this pi bond is going to go away, the carbon will have 2 hydrogens added, and this other lithium aluminum hydride has no more role to play with this particular molecule. The nitrogen, though, again has 2 lone pairs and therefore a negative charge, and that's going to be stabilized by the lithium. So the lithium is hanging around here, can sort of stabilize those. Okay, well, so much for the lithium aluminum hydride. The second step is water. You'll notice that we've added the 2 equivalents of the hydrogen to this, what you can kind of think of as the carbonyl carbon. Not officially, but the carbonyl carbon. You've added the 2 hydrogens there. It's like reducing an ester to an aldehyde and an aldehyde to an alcohol. That's where we're at now. So now we just need to stabilize this nitrogen with some hydrogens, do some proton transfers, and that's what this water is all about. So if you take this molecule and you treat it with water, the negative nitrogen can attack the hydrogen and do a proton transfer. So now, what we have left is the nitrogen has these sort of 3 bonds. Doesn't have a negative charge anymore. It's slightly negative though. And so another hydrogen can come in, or another water can come in and do another hydrogen proton transfer. This lone pair can attack that here. So you do another proton transfer. Amines in general are slightly basic. So what we have here is a hydrogen, and this nitrogen has a full positive charge. And what's happening is all of these electrons are repelling each other and pushing each other apart. And to help stabilize that charge, the aluminum comes off. So the aluminum gets kicked off. It was only holding on by a thread anyway. The only reason it ever came there was because the nitrogen was so negative. After these proton transfers, it's not as negative anymore, and so it pushes the slightly positive aluminum away. And you end up with that, and the aluminum with the lithium trailing along with it. But you'll notice that our product is exactly what we predicted, an amine. Now, oftentimes, you'll just have the skeletal structure. So it would look like this. This is the CH2 there. And so you get your product. Now that is the same as the product that we predicted above, when we just looked at it from the perspective of synthesis. So the long story short, what we learned in A is that if you treat a nitrile with excess lithium aluminum hydride and water, you end up getting an amine. Okay, how about B? Well, we have a bromine on this molecule, and when you see bromine, you should think awesome leaving group. In general, when you see the halogens, you should think awesome leaving group. And so with this first step, we're treating a molecule that has a great leaving group on it, the bromine, with a nucleophile. So this sodium cyanide, sodium is a metal, gives its electrons away to whatever it's bonded to. That's the carbon here. So we have cyanide, that cyanide ion. Because of that negative charge, it can act as a nucleophile and attack that carbon, kicking the leaving group off. So now, after that, we have this here. Remember that capital CN is really a carbon triple bonded to a nitrogen. Well, that's a cyanide. Now the next step is a little trickier. First I'm going to go through it just in terms of synthesis, and then we'll walk through the mechanism for that one. In terms of synthesis, when you treat a nitrile with a Grignard reagent, and that is what we have in this next step, you end up forming a ketone. Now I know this does not look intuitive, because you have a nitrogen there, and you end up having your 2 carbons. So those are the 2 carbons that are here already, but then that's going to be bonded to the methyl group of the Grignard reagent. And in between those 2, you will have a ketone. Now this is happening because of both of these steps, the Grignard reagent and the water, or the hydronium catalyst. It's actually the hydronium that is going to end up giving you this oxygen here. Well, that's our product. That's what you'd expect from this. Except in this one, you would, yeah, no, that's what you'd expect, sorry. So in this one, I want to walk through the mechanism for how that ketone gets formed, because it may not seem so intuitive. So what we have here, we've already gone through the mechanism for the first part, this SN2 reaction. So let's focus on this nitrile that we have and how that would react with the Grignard. So we have that nitrile,
and we treat it with a Grignard reagent, here methyl magnesium bromide, so it's just really a CH3 with a full negative charge, stabilized by magnesium bromide. What ends up happening here is similar to what happened with lithium aluminum hydride. The nucleophile attacks what you could normally think of as the carbonyl carbon, which is slightly positive because it's triple bonded to an electronegative element. And a pi bond breaks, and the electrons go on to the most electronegative place nearby. So you have that nucleophilic attack there. Now, after that, you have the two carbons. We're going to have a double bond to the nitrogen, which now has a full negative charge. So this had one lone pair before, now it has two and a full negative charge. But now you have the CH3 attached there, sort of like the hydrogen was when we used lithium aluminum hydride. And what you'll notice we have here is we're just two proton transfers away from having an imine. So after this attacks, we have hydronium, so we can do some proton transfers. We'll start with just one. Nitrogen attacks the hydrogen, the electrons go onto that oxygen. So we have this. And then we have our imine at this point. We also have water here. But you'll remember from the previous chapter that imines can react with water and hydrolyze to give you ketones. And that's how we're getting the ketone that we predict here. The water can come in, this carbonyl carbon is, or it's not a carbonyl because it's a nitrogen, but the imine carbon is slightly positive, so this oxygen, this water can come in, attack it, the pi bond can break. So we get a sort of tetrahedral intermediate. We can do a couple proton transfers to stabilize these charges. So for example, we could use a hydronium. Remember, this is the step that we're on. We have that hydronium wash. So we could do a hydronium to do a proton transfer here, stabilize that. We could use the water that we make there to do a proton transfer to stabilize what was our nucleophile. So that's another proton transfer just to stabilize that molecule. And then finally, we can do one last proton transfer with this hydronium that we make to turn the nitrogen into a good leaving group. So the nitrogen can steal one last, it can act as a base, steal one last hydrogen, and it will become a good leaving group. So it would have that full positive charge. The carbon in between is still slightly positive. It's bonded to two electronegative elements, so it's really slightly positive, and the lone pairs here can snap down and kick off that good leaving group, ammonia. And so what we'd have after this point is here's our double bond to the oxygen, which has a hydrogen on it, and we have the CH3. So notice this oxygen is now here, has the hydrogen on it still, but it has a double bond and a full positive charge, and this methyl group is here. And somewhere floating in solution, we have ammonia. Well, that ammonia can do one last proton transfer. It can steal this hydrogen, the electrons snap back on there, and what we end up with is the ketone. So that's kind of a review from last chapter, where we drew the mechanism for imine formation, but every step in that was reversible. And so if you have an imine, you can treat it with an acid and it will turn into a ketone. And you can see that that is the ketone that we predicted above. So in general, when you treat a nitrile with a Grignard reagent followed by acid, you will end up getting a ketone. On one side of the ketone, you'll have the carbon chain that you had in the nitrile, and on the other side, you'll have the carbon chain that was in the Grignard reagent. Okay, so much for that. For C, well, here we have a nitrile again, and we have a Grignard reagent followed by acid. So we just drew the mechanism for that. I won't draw that again. What we have is we replace the nitrile with a ketone. On one side, we have the same carbon chain we had before. On the other side, we're going to have the carbon chain in the Grignard reagent, so an ethyl group. And I'll connect these just in a skeletal drawing. Okay, so that's what we have after these first two steps, using the same mechanism that we used before. In step 3, we have lithium aluminum hydride, LaH, or LiAlH4, whichever you prefer. And remember, that's a hydrogen nucleophile. So that will, you have aluminum with the 4 hydrogens. The whole thing has a negative charge stabilized by the lithium's positive charge. So those hydrogens are more electronegative than the metal. They can take their electrons, attack the carbonyl in the ketone, kick the pi bond electrons up, and ultimately turn the ketone, reduce the ketone to an alcohol. Now after the first hydrogen adds, you have water after lithium aluminum hydride to stabilize the negative charge there. So this can attack that hydrogen, the electrons move, and you end up with that alcohol there. So I'm drawing the mechanism here. You wouldn't have to if this were a question on the test. These synthesis questions just require you to predict the product. But I wanted you to see how it would form in this exercise. Okay. Last one is the hydrolysis of nitriles. So here we're going to have a nitrile and we're going to use an acid catalyst to break it apart. Ultimately, this will just turn the nitrile, if you're just looking at this from a synthesis perspective, this will turn the nitrile into a carboxylic acid. But how does it get there? So it's just a one-step synthesis. But how does the nitrile, step by step, turn into a carboxylic acid in the presence of hydronium? Well, if you are interested, in case you are interested, I will draw the mechanism. The nitrogen here has that lone pair that can act as a base. So it steals one of the hydrogens from the hydronium, and the electrons snap onto the oxygen. After you do that proton transfer, you end up with a bond to a hydrogen here and a full charge on the nitrogen. After all, it has 4 bonds. Well, at this point, we can take the water that we made, and that water can act as a nucleophile. So, slightly negative oxygen can attack the slightly positive carbon here and push the electrons in one of the pi bonds onto the nitrogen. Remember, the pi bonds are really easy to break because you don't have that uninterrupted overlap that you have with a sigma bond. So, now we have an OH, or H2O rather, bonded onto this carbon. That oxygen has 3 bonds, and so it's got a full charge, positive charge. We have only 2 bonds to the nitrogen, which has a lone pair now.
Okay, well, another water molecule can come by and do a proton transfer to stabilize the charge on this oxygen. And I want to remind you, you're not responsible for knowing this mechanism. I'm just showing this to you so that you could see why this transformation happens. So, we'd have this now. An OH, 2 lone pairs there, double bond to the nitrogen. All right, so this is our molecule at the moment. Now, ultimately, we want to turn this into a carboxylic acid. This is, in the end, you will see this slowly transform into the carbonyl oxygen of the carboxylic acid. But what we get here at first is we need to get rid of this nitrogen, and so that takes another acid catalyst and acts as a base yet again, the nitrogen does, and steals a hydrogen from hydronium. The electrons snap back onto the oxygen there. So what we get after that step is a nitrogen with a full positive charge because it has 4 bonds on it. And that nitrogen actually exists as one of 2 resonance structures. This nitrogen with the positive charge, these lone pairs here are allylic to this pi bond, so you could sort of draw another resonance structure. Where the lone pairs go toward the pi bond and the pi bond breaks and goes toward the nitrogen. So in that case, the nitrogen wouldn't have the positive charge. It'd have the lone pair instead. And this oxygen would have a double bond, 3 bonds, therefore, and then, because of that, a full positive charge. So now you can start to see how this oxygen is going to turn into this carboxylic acid, carbonyl oxygen. Because a water molecule can come by, steal the hydrogen there, the electrons snap back onto there, and what you end up with after that proton transfer is this here. In other words, at this point we have turned the nitrile into an amide. Now all we have to do is acid-catalyzed hydrolysis of an amide, but that we've done in many, many videos. This was the reaction, this is how proteins come apart. So we've seen this before. Ultimately, this comes apart first by doing a proton transfer to put a positive charge there. Then the water attacks, so you get the water down here. This bursts open. You do a proton transfer to stabilize that. You do a proton transfer to make this a better leaving group. These lone pairs come down to form a pi bond, kicks the leaving group off, and you do one more proton transfer, and you would end up with a carboxylic acid. Now I went through that ridiculously fast, but that's because we've spent so much time on that in previous videos. So you can see ultimately you end up with a carboxylic acid in 2 kind of major steps. The first step is the nitrile turns into an amide, and the second step is the acid-catalyzed hydrolysis of an amide. But in terms of synthesis, what you'd want to remember is anytime you see a nitrile combined with hydronium or any sort of strong acid, it will turn into a carboxylic acid. So those are the reactions of nitrogen.